Introducing ConstraintJS, a system that integrates constraints in finite-state machines for the web. To illustrate what this means, let's look at this color selector programmed in ConstraintJS. And for now, let's focus on just one of these sliders, say the red one. We create a constraint variable named r to represent the current value of the slider. The CJS function makes this a constrainable variable, and the content of the function tells r how to fetch its value. We'll represent constrainable variables with the dot, and if we ask for r's current value, we get 190. We then specify when r's value might change, so that we know when to update its value. And the end result is that we have a constraint variable whose value is always the value of the slider. And we can do the same thing for the other color sliders as well. Let's create a fourth constraint variable named hex, whose value is constrained to the combination of rg and b. ConstraintJS figures out then when rg or b changes, hex will also change. We constrain the background color of the window to the value of hex, and also the text of the title bar. And like that, we have a live color selection widget. ConstraintJS also integrates finite-state machines with constraints. To illustrate why, let's look at the scatterplot example, and let's look at one point in particular. Here, there's some underlying model that the position of every point is constrained to. To put it another way, data flows up from the model to the graph by default. But this application also allows the data to be modified by clicking and dragging a point. So now, the underlying model actually has to have its value constrained to the position of the point on the graph. Or to put it another way, now the data has to flow down from the graph to the model. This is where the finite-state machines come in. Here, every point has two states, idle and dragging. By default, every point is going to be idle, and when it is, then the scatterplot point is constrained to the model, like before. But when the point is in the dragging state, its position is constrained to the mouse position, and the model's value is constrained to the scatterplot point. One thing to notice here is that in the idle state, the scatterplot point is constrained not only to the model value, but also to this variable called scale. We'll get back to that in a second. So here, for the point being dragged, the value flows downward from the plot point to the underlying model, while for every other point, constraints go the other way. In this application, you can also change the scale of the scatterplot by holding Shift while dragging. Here, the scales of the axes are properly constrained so that the point being dragged follows the mouse, but the underlying model doesn't have to change. While for other constraints, make sure all four of the axes labels have the correct value. And that reference to the scale variable when computing the point location allows every other point to move along with the scale automatically without the developer having to do any extra work. The axes themselves can be dragged, and constraints make sure that their labels have the correct value. ConstraintJS also works with third-party libraries. This bubble cursor example uses the Raphael drawing library. And it's not limited to mouse and keyboard interfaces either. ConstraintJS works just as well in touch interfaces and on the iPad as it does on the desktop. The layout of this photo manipulation interface is controlled by constraints as well. It also works with server-side JavaScript engines like Node. Thanks for watching. Please read the paper for more information about the ConstraintJS API, design, and implementation.